Okay. No, okay. Good morning. My name is David Houdoux. I am a third year PhD student, and my supervisors are Axel Hamon and Jean Crassou from Institut Physique de Rennes. And today I will talk about fluctuations of deformation inside a stationary shear band. So, first of all, let me remind you a very typical characteristic for granular materials. When you apply stress on a granular materials above a stress threshold, you have all the deformation which are localized inside. No. No. So above stress threshold, all the deformation is localized inside narrow bands, and outside these bands, the material is barely deformed, and we're able to reproduce this kind of behavior in the lab. So here it's an experiment. The granular material is confined, and we apply a force at the top. So at the beginning, the deformation is everywhere inside the sample, but above the stress threshold, it appears a band here, and all the deformation is inside the band. And the angle theta of the band is well described by the Moore-Coulomb model. So this angle make this relation true. So tau, the shear strength, must be equal to mu, the friction coefficient, times sigma, the normal stress. If you keep applying force at the top, in fact, you can see that the band is a shear band, and this band is stationary, and all the flow is localized inside the band. So today I will present you how in Rennes we experimentally get a stationary shear band, and I will show you observation of local strain fluctuations inside the band, and I will finish with a characterization of these fluctuations. So in Rennes we perform biaxial tests. So our system is made of glass beads with diameters around 100 micrometers. The dimensions of the samples are here. And first, we confine our granular material by pumping inside it. So we have a confining stress of 30 kilopascal, which is much smaller than is the Young modulus. So here we are in the case of a flow of hard tears. And then our sample can't move to the bottom, to the back, or to the front, and we apply a stress force at the top. This is a quasi-static compression with a strain rate around 10⁻⁵ per second. And inside our material, the cohesion is negligible. We observe rearrangements inside our material by using an optical technique, the diffusing wave spectroscopy. So in fact, we illuminate our sample with a laser, and we collect the backscattered light. And in fact, this is a speckle pattern. And when beads are moving, the path followed by the light is slightly modified, and as a result, the speckle pattern is modified too. So we can see how modifications occur by compute correlation between two successive speckle images. This is the quantity GI. And what is interesting in this method is the fact that we can make a link between GI and a function of the local strain inside our material. So we are able to measure local deformation epsilon in a range from 10⁻⁶ to 10⁻⁴ with a spatial resolution of around 3 diameters of beads. So now I will show you a movie of maps of local deformation for macroscopic increment delta epsilon 3.5 10⁻⁵. So this is the macroscopic increment between two successive speckle images. And when you have a bright pixel, it corresponds to a small deformation 10⁻⁶, and a dark pixel corresponds to a bigger deformation. Up. Sorry. Okay, so here we keep applying a stress at the top, and we have above the stress threshold, and you can see that almost all the deformation is localized inside bands, and outside these bands, in these blocks, there are no deformation. With our optical method, we are able to make bit tracking, bit trackings, and we are able to get the displacement map of our sample. So we can see that the block at the top is translating to the bottom, this one to the left, this one to the right, and the block here doesn't move. So we can see that the deformation that we observe in these bands corresponds to shear. Now we can make the same thing, but we decrease the macroscopic increment. So now we take delta epsilon equal 5.710 minus 7. And here this is what we get. Okay, so we still see the shear bands, but inside shear bands we have fluctuations. And now we can ask, in fact, we want to know if these fluctuations are microscopic shear or something else. We want to know, as we can see, fluctuations are some localized inside the shear bands. We want to characterize this localization, and we want to know if there is some temporal correlation between these fluctuations. But first of all, we can say that there are fluctuations inside the stationary shear band. So first, we can take these maps of deformation for the increment deformation of 10 minus 7. We can make an average of the logarithm of this quantity, and we get this kind of maps. In fact, the logarithm of this quantity is directly proportional to the local deformation. So we can plot the profile of the shear band along the transverse direction z, and we get this profile, and we have a well-defined exponential decrease. And with an exponential fit, we can obtain the width of the band, 2 tau equal 18 diameters of beads. But as we know that the deformation is shear, we can make a link between the relative displacement between two blocks with the local deformation. So this is just the integration of the local deformation. We get this displacement, and the value for z equal infinity gives us the relative displacement between two blocks here. And we measure a displacement for this increment, a displacement of 17 nanometers, and we can compare this value with the displacement that we should get according to the angle of the band and the strain rate that we imposed at the top. And we should have 29 nanometers. So the two values are very close, and we can say that fluctuations are almost entirely macroscopic shear, because when we make an average of the fluctuations, we obtain the macroscopic displacement. Now we can again study these maps of deformation. We threshold the images, and we are able to detect individual events, which corresponds to our fluctuations. And we are able to determine the barycenters, the position of the barycenters of these events. So here I plot the dispersion of barycenters for this region of interest. And we can see that almost all barycenters are very highly aligned along a straight line, which correspond to the shear band. And if we plot the distribution through the band, so in fact the number of barycenters according to the distance from the center of the band, we can see that almost all barycenters are localized at the center of the shear bands. And if we make a Gaussian fit, we have the full width at half maximum equal 4.5 diameters of bead, which is smaller than the width of the band. So here we can know where our barycenters are. Um, Finally, we can try to calculate to make a kind of temporal correlation function. Here I take one map of deformation at instant epsilon, and I calculate the correlation with the same kind of maps, but at another deformation, epsilon plus d epsilon, and I change the value d epsilon. So this is this kind of correlation function, and I can plot it versus the strain gap d epsilon, and we have a well-defined power law for over 3 decades, and this quantity can be seen as the probability to get an event at the same place according to the strain gap d epsilon. And we can see that there is a memory effect in the occurrence of the plastic activity inside our granular material. So as a conclusion, we have seen that there are fluctuations inside the shear band. These fluctuations can be seen as individual events, and these fluctuations are almost entirely macroscopic shear, because when we make an average of the fluctuations, we get the macroscopic displacement, and these fluctuations are highly aligned along the shear bands with a full width at half maximum of 4.5D, which is smaller than the width of the band. And we can see that there is a memory effect in the occurrence of the plastic activity. Thank you for your attention. Yeah, at the same position. Uh, um, Along the shear band, no, no, not yet. Just at the same position for the moment. But think it's. I don't know. Okay, I don't know the result. This one. Sorry, I don't. Um, no. I don't know. No. A characteristic distance, I don't think. Yeah. Between. Yeah. Okay. Yeah. 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 But là, I focus only at the permanent shear.